In this video, we will review some function ideas covered in grade 11. So just a reminder about some of the general function ideas. We'll start off with a relation. So a relation is a set of ordered pairs x comma y. So you can see the ordered pair here would typically give you the coordinates of a point on a graph. We'll talk about that in a second. They are in alphabetical order. X comes first, followed by the y value. But a relation is not just one ordered pair, it's a set of ordered pairs. And you can see here, I've listed a set of ordered pairs. In math, we typically use these curly braces here, brackets, as an indication of a set. So this is a set, and you can see that within this set are four different ordered pairs. So this would make up a relation because it's a set of ordered pairs. Now we can express that set in a variety of different ways. We can express it as a set, as you can see here. We can express it using a table of values, so where we have an x and a y. So the x values would be listed down the left-hand side of the table, and the corresponding y values would be listed on the right-hand side of that table. So I'll just list those ordered pairs here. So we've got 1, 2, 4, 7, 3, 5, and 1, 4. Now the other way that we might express this is what we would call a mapping diagram. So we would have our input values. So our input values are the values that we start with, and they would be mapped to a certain value. So these would typically be your x values. So I could list my 1, 4, 3, and I've already got 1. So you can see here that 1 appears twice. It appeared here at the beginning and here at the end. So I've got the 1, I've got the 4, and I've got the 3. And then the y values we'll list over here. So we've got a 2, a 7, a 3, and a 4. So the 1 maps to 2, the 4 maps to a 7, the 3 maps to a, whoops, this should have been a 5 over here, sorry about that. The 3 maps to a 5, and then the 1 also maps to a 4. So that would be what we call a mapping diagram. This one tends to go, because of the way I built it just moving from left to right through the ordered pairs, so the points tend to kind of go across from each other. They don't necessarily have to do that. All right, and the other way that we can look at a relation is by looking at a graph. So you can see here, we plotted the point 1, 2. That's right here. That's the first point. The point 4, 7 is over here. The point 3, 5 is here. And the point 1, 4 is here. So you can see those 4 points make up our relation. Now we're going to talk very briefly about functions here. Notice we'll come back to this idea in a second, but I want you to notice this connection here. You can see here that right along this line, if I were to draw a line, why don't I try to do that? If I were to draw a line right here, you can see that those 2 points would both fit on the line. And that'll be important in a second when we talk about the vertical line test. So let's move on to the next page. We'll talk about functions. So a function is a special kind of relation. It's a relation where each value of the independent variable corresponds to at most one value of the dependent variable. An easier way to think about that is that each x value can only have one y value. So I've listed 2 relations here. You can see them. One looks a little bit longer than the other. And in the first one, we have an x value of 3 going to 5. We don't see a 3 appear in this list again for an x value. 6 goes to 7. There are no other 6s for x values. 4 goes to 8, no other 4s. 5 goes to 11. 9 goes to 13. 10 goes to 12. You can see here that there are no duplicate x values. So this actually would classify as a function. This would be a function. And it's a function because every x value corresponds to only one y value. I should say at most one y value. Whereas if we look at this second relation, you can see here that when x is equal to 3, y is equal to 7. But further along, we can see that when x is equal to 3, y is also equal to 4. So this is an example of a relation that is not a function because it doesn't satisfy the condition up here that every x value can only have one y value. Here, the x value has 2 separate y values. The x value of 3, has a y value of 7 and a y value of 4. And there may be other situations. I don't think there are in this case. Oh yeah, here's one right here. 9 and 12 sort of break that condition. So the first one was a function. This relation here certainly is not a function. And I talked earlier about this vertical line and how we pass through the vertical line twice. This is an example where x equals 1 has two y values. It has a y value of 2 and a y value of 4. So this relation that I listed on the first page is actually not a function. Let's look at a couple more examples here. And we're going to look at this thing called the vertical line test. So the vertical line test basically tells us whether a function is a relation or not. So if a relation, passes the vertical line test, then it is a relation. Let me word that again. If a relation passes the vertical line test, then it is a function. And what do I mean by the vertical line test? I basically mean that you draw a vertical line. That's not a very vertical line. Let me try that one more time. If you draw a vertical line and you drag that vertical line from left to right across the function, you see that the function only crosses at one spot. So I can look here and see that the vertical line and the function meet only in one spot right there. If I keep sliding my vertical line along from left to right, you can see that it only meets the function in one spot. So this parabola passes the vertical line test, and as a result is a function. So this is a function because it passes the vertical line test. If I take that vertical line over to this relation over here, this circle, I can see at most of the places on this circle, we actually end up crossing or meeting or intersecting the vertical line twice. And that right there makes this not a function. This relation fails the vertical line test, and as a result is not a function. Let me just dot down that is not a function. So that's a quick way that you can tell just by looking at the graph whether something is a function or not. If you need to look at the table of values, then you can use the example that we used up above. All right, moving right along with our function review. We can represent functions in a whole bunch of different ways. We've already looked at a graph. We've looked at a table of values. You can also look at an equation, an algebraic model, and a real-life application or a contextual model. So this is the graph of y equals 2 to the x. You can see it here. It means it has a slope of 2 and a y-intercept of 0. You can see that y-intercept here, and you can see that the slope is 2 because we are increasing by 2 every step on the graph here, where we're increasing by 1 over here. So just a reminder, slope is just the rise, how much are we going up by, divided by how much are we going over by. So here we were going up 1 every time. So our slope here is equal to 2 over 1, which is just equal to 2. And the y-intercept is the point right here on the graph where the graph crosses the y-axis, or the y value when x is equal to 0. So the y-intercept, we often call that a b value, but for right now we'll just call it the y-intercept equals 0. So the equation here would be y equals 2x. So that's the sort of how do we get from the table to the equation. We'll do a lot of that in this course, probably for a bunch of different functions, but it's helpful to kind of review what does that look like for a linear function. All right, and the other thing I think that we need to talk about is function notation. So in grade 10, you learn about the parabola. You write the parabola in this form, y equals x squared. It's a relationship. It's that sort of, if you wanted to draw this and see what it looks like, you could make a table of values. Let's go -2, -1, 0, 1, and 2. -2 squared is 4. -1 squared is 1. Keep doing that. 1 squared is 1. 2 squared is 4. And then we could do a sketch of this and we'd get that parabola that we saw on the previous page look like this. Now, the other way that we can express this is in function notation. So this is what we call function notation. And basically, with this function notation, we just give the function a name. And in this case, the function was called f. It doesn't have to be called f. It could be called something else. It could be g. It could be m. It could be anything we wanted to. It's just a name that we're calling our function. And then the way that we read this is just f of x equals x squared. And the idea here is, the nice thing about this form is that if I wanted to evaluate the function at a certain value, I could just say, well, what is f at 2? So what is the function value this when x is equal to 2? So this would be x equals to 2. What is the y value? That's kind of what this is asking. What is the y value? And we'll do a little bit of practice. I've got a couple of examples on the next page here for us to have a look at. So let's have a look here. Here's a function, f of x equals 3 bracket x minus 2 all squared minus 4. And the question here is to evaluate what f at 2 is. Well, f at 2 means that find the y value when x is equal to 2. So f at 2 means substitute a 2 into that equation everywhere we see an x. So x is going to be 2 minus 2 squared minus 4. And then we can just do the arithmetic here. Remember the order of operations. We'll do the brackets first. 2 minus 2 is 0. This part right here is 0. 0 squared is 0. So really we get 3 times 0 minus 4. It would give us negative 4. And again, here's the same sort of thing, except now we're substituting a negative 3 in everywhere we see an x. So the function here becomes 3 bracket negative 3. Again, everywhere we see an x in that function, we're replacing it with the value that we see in our inside the brackets here. So we get negative 3 minus 2 all squared minus 4. And again, we'll start in the brackets. Negative 3 take away 2 will be negative 5 squared minus 4. And then here, negative 5 squared will be 25. 25 times 3 is 75. Subtract 4 will be 71. And, sorry, that's not a great looking one. We can evaluate the function for any value. So here we did it for a positive number. We did it for a negative number. We can also do it for a fraction. Here's a good review for your those of you wanting to brush up on some of your fraction work. It's a good opportunity. Oh, we are evaluating f at 1/3. I forgot to put my 1/3 in there. So everywhere we see an x, we're going to replace it with a 1/3. So we're going to get 3 times 1/3 minus 2 squared minus 4. All right, here's our fraction practice here. So this is I'm going to keep the 3 over there. We need to do the work inside the brackets first. I can't subtract the fraction and the whole number until I have a common denominator. Let's see if we can do that here. So the denominator here is a 1. I want it to be a 3, so I need to multiply the denominator and the numerator by 3. And I will get 6/3. Many of you probably knew that already, but I just wanted to show you what happens. Don't forget the squared there. All right, let's do this. So now we can do 1/3 minus 6/3. Remember the way that we subtract fractions. Once we have that common denominator is to subtract the numerators. 1 minus 6 will be negative 5/3. Don't forget the squared and subtract 4. We'll square. We'll do the exponents after we've done the brackets. When we square a fraction, we square the numerator and we square the denominator. So this is a negative number. A negative number squared will be positive. 5 squared is 25. 3 squared is 9. and then we'll multiply that by 4. All right, we're getting close to the end here. 3 times a fraction. Remember, the way that you multiply fractions is to multiply the numerators together and multiply the denominators together. So 3 times 25 will give us 75. And then 9 times 1 will give us 9. And we're so close. The last thing that we need to do here, I just ran off the edge of my page here. The last thing we need to do is to find a common denominator. Just subtract these two. That common denominator is going to be 9. I might run out of space here. So we get 75 over 9 minus 36 over 9. And again, just a reminder, when you subtract fractions, keep the denominator and subtract the numerator. So 75 minus 36 will give us 39 over 9. And can we reduce that? We can probably divide by 3 in both the numerator and the denominator. 39 divided by 3 will give us 13, and 9 divided by 3 will give us 3. So 13 thirds is what we're looking at. So a little bit longer with the fraction, only because we had to do some of that work with common denominators, but hopefully you get the idea. The last one here is maybe a little bit different, but we can evaluate this function at any value. It doesn't matter if it's a positive, a negative, an integer, or even a variable. We can evaluate this function at when x equals a. So f at a just means substitute an a into all of the values of x in the equation. So 3 bracket a minus 2 squared minus 4. Now notice there's an a in this equation or this function. There will always be an a until you give me a value for what that a equals. And we can probably just leave this here. We could probably expand it, collect like terms if we wanted to, but this is an acceptable representation for f at a as well. So that's a review of some of the introductory function stuff, just to make sure that, that you have that stuff before we